Good evening to one and all. आप सभी को नमस्कार. On the behalf of Department of Mechanical Engineering, KIPM College of Engineering and Technology, GIDA Gorakhpur, I extend a warm and cordial welcome to all participants, distinguished speakers, and esteemed guests as we commence the 5th day of our ATAL Academy sponsored faculty development program on title Towards Sustainability: The Role of Advanced Materials in Next Generation Engineering. The overwhelming participation and enthusiasm we witnessed on the previous day have truly set a positive tone for this program. Yesterday's session were highly insightful and enriching our understanding of sustainable technology and innovative research approaches in advances prescribed and sustainable photovoltaics, given by Mr. Rahul Patel sir, Assistant Professor, Department of Mechanical Engineering, KIPM GIDA. Today, we continue this journey of learning and exploration with renewed energy and curiosity. We are privileged to have eminent resource persons who will share their expertise on recent developments in sustainable materials and energy system, which help us bridge the gap between the research and real-world application. I once again welcome everyone to this day of intellectual engagement and collaboration. Let us make the most of these sessions and continue fostering the spirit of academic excellence and innovation. So thank you and welcome to day 5 of our FDP. Now, before proceeding for the session 1 of this day 5, I would like to take a little time to share a brief introduction of our speaker for this session. It is indeed a great pleasure to introduce Professor Ajay Kumar Yadav sir, who is a distinguished leader and visionary in a field of mechanical engineering. Welcome, sir. It gives me immense pleasure to welcome you all. Session 9 of our faculty development program on Towards Sustainability: The Role of Advanced Materials in Next Generation Engineering. Today, we are privileged to have with us a distinguished academician and researcher, Professor Ajay Kumar Yadav sir, who is Associate Professor in Department of Mechanical Engineering at Indian Institute of Technology, Patna. Professor Yadav is a renowned scholar in the field of thermal sciences, renewable energy, and heat transfer system. With an impressive academic and research background, he has contributed extensively to the area of solar thermal energy utilization, heat exchangers, and energy efficient technologies. His research publication in reputed international journals and his involvement in various sponsored projects stand as a testament to his expertise and commitment to advancing sustainable energy solutions. In today's session, Professor Yadav will deliver a talk on thermal therapy of cancer tumor cells, which focuses on latest development, design innovations, and performance optimization techniques that are shaping the future of the technology. His insights will provide us with a deeper understanding of how emerging technology can enhance the existing system. Let us extend a warm welcome to Professor Ajay Kumar Yadav sir and look forward to an engaging and intellectual stimulating session ahead. So the platform is over to you, sir. Welcome, sir.
Thank you for very lengthy introduction. It may not be needed. This is small introduction is sufficient.
No, sir. Okay, my pleasure.
So I'll share the PPT, and I think it is of 7:30. It will up to 7:30, right?
Yes.
Time? 7:30 timing, right?
Yes, sir. Yes.
Yes. Okay. So just confirm whether it's visible or not, my PPT. Can you confirm whether it is visible or not?
Yes, sir. It is visible, sir.
Visible. Okay. Just. So good evening to all of you.
Good evening, sir.
All participants, and thank you. And thanks the organizers for inviting me to deliver talk on this. Actually, day before yesterday, I delivered talk on solar thermal collectors using supercritical CO2. Actually, this FDP is on advanced material. So here actually the material part is nanoparticles, what I have used here for the thermal therapy of tumors. This is slightly different topic, and advanced material only that magnetic nanoparticles you'll be able to find here. But this is slightly different, and I hope you will find interesting in this.
Yes, sir.
So we'll start thermal therapies of cancerous tumors. So first is the cancer, everybody knows about this cancer. Okay. So we'll go one by one slide. Okay. So the thing is still the whatever the technology we have developed technology for treating the tumors, cancer. But still this disease, cancer, still remains a major threat to human being. And India, in only India, recorded 1.46 million new cancer cases in 2022. What data available I put here. So you can see around 15 lakh in 1 year cases reported. In that, there are oral, breast, cervical, different types of cancers altogether. But these things, oral, breast, and cervical, is most prevalent. So cancer-related deaths in India numbered approximately around 8.5 lakh that year. So you can think that every year 15 lakh cases coming, and death also around 9 lakh. 60% death is there. So really very threatening this disease for human being. So nowadays, due to advancement in imaging techniques and technological developments, thermal therapies are being used to kill cancer cells, mainly in solid tumors. But in India, still this is not that much widely used. So, and this technique, the thermal therapy technique, is not that much, not painful, you can say that the other techniques what we use, chemotherapy, radiation therapy, and surgical part. First you do the surgery if possible, then chemo and radiation are very, very painful, you know that. And this data I have put some earlier cases, and you can see here in 2004, the case was 8 lakh, and 2022, it reached almost double, 15 lakh, 14.6 million 2022. So this day by day it is increasing. Another thing is you can see that number of cases in males and females. Females having more cases in the cancerous cases. The reason is one is breast tumor, additional part. Okay, so the more cases are in female. If you see the total and male female both data. And what is actually this? What is this cancer tissue? Why? How it happens? Those things. There are many research going on. Some type of cancer still we don't know why it happens. Okay, and some types of like mouth cancer, some type of things, lungs. So those things we know. And major part of if you differentiate cancer cell and normal cell division is slow and cancerous cell division is very fast, uncontrolled way division will take place. Okay, and the thing is once if you are able to detect at early stage, then it can say it is curable type early stage if it is detected. But the people think that may be due to some gas problem, this problem, normal problem, and that gets prolonged for 1 year, 2 years, and that will go in the higher stage. then it is very painful, and that recovery or getting treated 100%, it is difficult. There is a chance of reoccurrence. After maybe few years may happen again. Okay, so these are the cancer therapy. In that there are many techniques. My part, what I am going to focus today is on hyperthermia part. In that mainly thermal therapy of tumors. In thermal therapy, there are two things, hyperthermia and hypothermia also. So that part we will talk on that. So, sorry. Thermal therapy or thermotherapy, also called hypothermia, is a type of cancer treatment. Actually, hypo and hyper, generally hyper refers to the higher temperature. Hypo means lower temperature. Okay. Hyperthermia generally 5 degree, 45 you can say, around 37 plus 5 if you go, that will go to 42. 42 to 45 means 41 to 45 is treated like a hyperthermia case, and hypothermia is the negative side. So what is this thermal therapy main? I'm explaining this. What is this actually? Is we are heating the tumor and killing it. Very simple way. If I say just heat it and burn it. Burning means that much high temperature we are not going, but if you burn it means it will completely permanently it will get killed. Cells will get killed. But it is not easy to do that. If you are heating, supplying some current and heating it, some sources, the normal tissue, healthy tissue also gets heated. It's not easy to do that. Okay. So the different techniques we will talk on this. So the thing is, in thermal therapy, second line you can see the heat is used for the treatment depending on the whether your heat you are supplying or heat you are removing. So if you are heat removing like hypothermia type of things, in that cryoablation will come. You are cooling and killing like that actually. Cooling means you are going minus 50 degrees Celsius. Actually, in this case, cryoablation is there. We use liquid nitrogen. Liquid nitrogen temperature, 77 Kelvin. And maintain the tissue temperature minus 50 and below. So if you use that temperature, what happens? Near tissue, there is a water always there in the body. So that gets frozen actually, that will become solid. And when it solidifies, what happens? The volume will increase. And when volume will increase, that tissue will get stretched, you can say. So in that way also it gets damaged. So that is the cryoablation part. Many places, skin disease, upper surface means the surface part, that getting treated using cryoablation. Thermal therapy is a treatment in which target tissue is exposed to the heat to high temperature. Okay. So that one is cryoablation, low temperature, and thermal part, this is hyperthermia side is a high temperature. So in that there's a, if you are operating 45 or less than 50, in that range, that is called hyperthermia. Otherwise, if it is above 50 degrees Celsius, that is called thermal ablation. Thermal ablation, you can see here, greater than 50 degrees Celsius. So this will give, if you operate at higher temperature, that will give irreversible damage to the tissue. Again, reoccurrence is like impossible type of things. Okay. So in this, how it gets damaged, actually, some are biological terms here, hyperthermia. So protein gets damaged. With that, actually, these are the things: membrane damage, nuclear protein damage, inhibition of cell proliferation. Actually, our part here is tumor cell death. There are two ways. One is low heat damage. Low heat damage is called apoptosis. Okay, and high heat damage if you are giving high dose, then that is called necrosis. So we will talk about the necrosis percentage and all things. Okay, cell death, we'll find out and we'll do that. So here I have put some here temperature range for the different types of therapy, thermal therapy. So cryotherapy, you can see here the minus 50 degrees Celsius, first one you can see. And thermal ablation is greater than this 47 to 50. If you are operating 45, then that is hyperthermia, and above that is 50, generally 50 and above, you can say in that range, that is thermal ablation. Then different types of hyperthermia also there, moderate, low temperature, this type of things. Okay. Here, if you see the temperature range I have given here, if it is at around 37 to 40 degrees Celsius, homeostasis, that is called, slightly higher temperature. 42 to 45, this is the hyperthermia type of range, 42 to 45 hyperthermia. So if you are hitting tumor cell at this temperature, this tissue will be more susceptible to chemotherapy or radiation therapy. At higher temperature, first you increase the temperature, so some part of the tissue will get damaged, and again you put on that radiation, then complete damage you can expect. Okay, more damage you can expect. So this is the thing, hyperthermia can be, you increase the things, then you give chemotherapy or give radiation therapy, then this will be more effective. Above that, if you go 50 and above, irreversible cellular damage you can see, instantaneous protein coagulation will occur, and ideal temperature of ablation, thermal ablation. So this is around 100, it is going, and above 100 it should not go generally. Then that, what will happen, that charring will happen. That is, it will burn and carbon type of things, or vaporization, carbonization, that will occur. So if that occurs, then your impedance will increase and there will be problem in this system. So we should control that. We should not go that much temperature. Okay. So energy sources, what the people have used and being used, microwave, this is one thing, radio frequency, laser, ultrasound. Okay. In the radio frequency, there is a RFA, radio frequency ablation system, and magnetic fluid hyperthermia, also there in the radio frequency range only. So heating mechanism is the thermal conduction. Heating mechanism, mainly what happens here? You are supplying current, and with the Joule effect only it is getting heated. Okay, now the thing is, there are challenges in that. You are heating that, but only the tumor tissue should get heated, not the surrounding tissue, healthy tissue. So that challenge is there. So radio frequency ablation, in this we use one syringe type of structure. I will show you that in the later. And we suppose tumor is there someplace here, and you can put that syringe type of things, electrode, and it will go inside, and in that will supply current at high frequency, and heating will take place in that, near to that electrode. So this is the one thing, that is radio frequency. And then similar way, microwave also, that it will go antenna type microwave inside only, microwave also. Laser, ultrasound, these are the different techniques also. Okay, so this part, normal tissue and tumor tissue, what is the difference? If you are heating a normal tissue, what will happen? Generally, that our system is like that. Hypothalamus we have in brain, and our system is like that. If somewhere temperature is increasing, that will try to balance it. So if it is normal tissue, if temperature you are increasing, then what will happen? The blood flow rate will increase automatically. It will increase so that the temperature rise, it will try to diminish that. But in the tumor tissue, that will not happen. So if you are increasing the temperature, blood flow will not increase. So this is a good thing for us. If blood flow increases, then what will happen? That heat will be carried away from the tumor to the body. That is not good. We don't want to heat the body. We want to heat only tumor. So this is a good thing for that. Okay. Okay. So during RFA, one or more electrodes are inserted into the tumor tissue with the help of image guidance technique. Okay. So, sorry, based on the location of tumor, using some image ultrasound or CT scan or something, you have to insert that electrode. Electrode are single-tined, multi-tined also. In that inside there will be multi-tinds. I used 9-tined. 9-tined means 9 wires will be there inside. And that first you put inside, then you rotate, then it will become like this. So 9-tined, so that it will cover more volume, more area. Then once it is positioned, then you can start the current supply. High frequency alternating current here need to supply that. 360 to 500 kilohertz is the radio frequency in that. This range is a high frequency current we supply. Actual heating of tumor is done due to Joule effect only. Okay, and from one part to another part it will go, means throughout the tumor heat conduct due to heat conduction only. Okay. So coagulation begins at 43 to 45, but the desired damage can be obtained at high temperature greater than 50. Increase in temperature around 100 to 105 leads to charring of tissue and sudden increase of impedance. So we should avoid that. We should not go to that. Yeah, now you can see this. This is the, you can say, RF generator. And this is electrode, and this part tumor is here. Okay, electrode you are putting in this. This is the single tined. Okay, if you there are multi-tined also to cover the larger tumor. Tumor size is large, more than around 2 centimeter or 3 centimeter. So then multi-tined we should use. So this is the grounding pads. On one side you are supplying current at high frequency. You can see here also grounding pad you can put. One thing is why we use high frequency current. Why not normal current if you supply? There are some challenges here. Normal current if you supply, what will happen? This 50 hertz current. Even low frequency current, what happens if you supply low frequency current? Just some example. This is a conductor solution. Okay. You are supplying some current here. If it is DC, what will happen? This will be, the charge will get distributed homogeneously, right? Throughout this cross section, it will flow through this. If you increase frequency, what will happen? This charge will migrate towards the surface. So as you increase the frequency, so charge will or current will start flowing on the surface. This is called the skin effect. Okay. So in a body, if you are supplying 50 hertz, it will go through the internal part also. And this can cause the damage of the other internal organs. Okay. So that is the major part. We cannot use 50 kilohertz and below frequency for the treating the human being. 50 kilohertz and above we should treat. So that's a one challenge. You have to use frequency generator, get higher frequency. Then at higher frequency, you have to maintain the power also, voltage and current. So this is not easy task. Okay, there's also challenge involved in this. So what type of equation we solve here? Payne's bioheat equation. Payne's bioheat equation, this is the heat transfer equation. In this extra term is blood perfusion rate. This is the perfusion, means if blood flow is there in that, and metabolic rate, QM. And QS is the source term or the heat you are supplying there due to the Joule effect. So that QS you can calculate from the here, how much electric current or voltage is there. Based on that you will get this QS. And the last one, tissue damage, how much tissue got damaged, that how to calculate using the first order Arrhenius equation we are using. Okay. So effect of electrothermal parameters on lesion formation during radiofrequency ablation in different tumor tissue. So this small study we have done, actually it was 5 years back result. So a M.Tech student did this. So we have done some simulation using COMSOL software. So in that 3-dimensional numerical study we have done, and using different types of tumors, liver, kidney, lungs. Okay. So the effect of tumor size and location of tumor on lesion formation were studied, and the effect of electrical conductivity, thermal conductivity of tissue. These properties of the tissue is available in the website, in the journals, and some published data already there. So that we are using and doing that. And we have done some experiment also, but experiment data is not here. You can make this phantom similar tumor type of properties using some chemicals. Okay, with that phantom you can make, and we did some experiment on phantom also. That is in vitro studies. In vivo we have not done. So this is you can see the tumor here. Some model we have assumed this 3-dimensional model, and tumor size is around different types of tumor size we have taken. Spherical tumor we have considered, but the thing is actual tumor may not be spherical. This is just one study, but maybe the different 15 mm, 25 mm, 35 mm, three sizes of the tumors we have considered. This is the diameter 15 mm, 25 mm, 35 mm. Means 1.5 centimeter, 2.5 centimeter, 3.5 centimeter. Ever 3, it is difficult to treat using these techniques. It is so we can use in that case some nanoparticles, so that the homogeneous temperature distribution we can get by increasing the conductivity of the effective conductivity of the tumor tissue, because we are injecting nanoparticle in that. So there are 3 studies here, and this electrode size what we are going to insert in that, this is 2 mm diameter electrode. Okay, this you can see, this is the electrode. It is not holding like that, it is like the electrode we have inserted in this, and this tumor size will be different, 15, 25, 35. Okay, and this study was done for voltage 35 volt to time 20 minutes. We are supplying 35 volt 20 minutes. Then resistance and all things was given based on the lungs, liver, kidney tissue. So you can see the here profile also. This is the temperature profile here. You can see temperature profile, lung, liver, kidney. That depends on the blood perfusion rate. Kidney blood flow rate is more. We know that. Liver, it is slightly less. It's much less. You can say slightly less. But lung and liver, if you compare, lung has very low blood flow rate. So if blood flow rate is less, then you will be able to get higher temperature using the same voltage. Okay, because the heat dissipation will be less in that. Going out, heat loss will be less, you can see. So that's why you can see here the temperature will be more in the lung than liver liver will be slightly less, little bit, and kidney is very less this way. This thing lesion formation means there are different techniques to find this lesion formation. So one thing is if the temperature of the tissue reached 50 degrees Celsius, then we can consider this is 100% damage, you can say, or lesion formed, not 100% damage, lesion formation. So wherever the 50% area covered, 50 degrees Celsius temperature rise, reached 50 degrees Celsius, those area if you find, mark it, then based on that, we have put here the lesion formation volume, or you can see area here in the 2D geometry area you can see. So kidney is less area you can see always, and this side lung, liver is more area. Temperature profile, if you see the similar way, lung, liver, kidney has very low temperature, you can see temperature profile compared to these things. Here also we have done some similar thing here at a different temperature range, different locations. At a different location, what is the fraction of necrosis, and what is the temperature part, and necrosis depends on the temperature only, you can say. So necrosis means type of cell damage. So necrosis, if you are finding here, A is the liver, B is lung, and C is kidney. So kidney, if you see here, even the three, we are seeing the diameter 15 mm. There are three types of tumor we have considered. 15 mm, two cases here considered. 25 mm, two cases, three cases. 35 mm, two cases. So 15 mm in the case of this liver part, and 7.5 mm distance, what is the temperature profile, or based on that necrosis you can say. So 7.5 means from the center is 0, 0. Center to 15 mm is the diameter, but you are going to 7.5 mm. From okay, so 7.5 mm diameter if you are taking from the center, it will be around 3.75 around. Okay, so in that, at that point, what would be the necrosis, what would be the temperature mainly. So if higher temperature, higher necrosis type of things like that. So you can see this graph here, how much time it takes to reach this 100% damage, like that fraction of necrosis tissue. So these are reaching like here, but in the case of, if you see the kidney case, this is the kidney case. Kidney case, you will not get this. These are the things actually. In the kidney case, special part here is 3.75 taken. Otherwise, you will not get this 100%. It is 3.7 very core inside. Here 7.5 result you can see in that case of liver and lung, but here 7.5, if you see, this result is coming here 7.5, very bottom, not reaching the temperature, or fraction of necrosis is very less. So like that. This part is actually of breast tumor. Actually, I removed the breast tumor part study because there are many data. So in that there are gland, muscle, and fat. There are three layers. In that, how much temperature you can reach. This is the for that, okay, how much time you need. Suppose 5 minutes, within 5 minutes you are able to reach this much temperature. Blood perfusion rate is also less in this, so easy to reach the temperature. Here you can see the effect of blood perfusion rate is showing here. So as you increase the ablation volume is how much tissue got damaged, you can say like that, or the tissue got ablated. What we are doing it radio frequency ablation system. So this is the ablated, means to say how much tissue got damaged type of thing. That. So if you increase the blood, here it is 0% blood perfusion rate. So you are reaching around this much ablation volume, 140, that range. Sorry, lung, liver, and all things. You can see the maximum is there. Time is fixed, 20 minutes. So in that 20 minutes, how much ablation you can get? Here, 25% if blood flow rate is there, then this much. Slowly, as you go 100%, then ablation volume is less. This is the effect. And this both are similar thing, but the way of calculating the ablation volume is different. This is IT isothermal temperature 50 degrees Celsius were reached. Based on that calculated. This is the Arrhenius equation using this omega is equal to greater than 1, where the omega is greater than 1, that volume is taken. Okay. So here the effect of electrical conductivity and the effect of thermal conductivity. So if it is very simple. If it is more, you can see this fraction of necrosis here. This ratio is taken just. Okay, just this one, I think this is the ratio is taken 0.143 by 0.5. So we will see the data maybe the next. So it is not there. Okay, maybe we'll see that if it is there in the data. So based on that, actually electrical conductivity and thermal conductivity, how this will affect the temperature. So if that is very simple, if there is thermal conductivity is higher in the tissue part, the thermal conductivity is higher, your temperature gradient will be less. So temperature differences you will not find much, homogeneous temperature you will get. So we need higher thermal conductivity of the tissue, but it is not like that. Higher thermal conductivity will not get. So what we do, we increase, we put some nanoparticle in that to increase the thermal conductivity. So that in the tissue part, only tissue part we should inject the nanoparticle, not the other part. Otherwise, other part also will get heated. So tissue part, tissue means to say cancerous tumor part only we should get. We should inject that nanoparticle so that your conductivity will be higher, and near the electrode tip, the temperature should not be very high, so that will get heat will get dissipated, okay, from the tip to the tumor's remaining area, further area. Now the thing is, whatever we have seen here, the problem occurs if where the electrode you are injecting, inserted electrode, and near the electrode the temperature will be very high, and just little bit away from the electrode temperature will be low due to the low conductivity of the tumor. So how to take care of this? There is a nanoparticle assisted thermal therapy. So you can inject a nanoparticle, and if you nanoparticle has that is the metallic nanoparticle, okay, iron oxide, gold, this type of things. So higher thermal conductivity is the metallic part. So that if you use, then you will get uniform temperature profile. Okay. So you can see this nanoparticle, and this is without nanoparticle part. So in that nanoparticle also there are many techniques. One is nano radio frequency ablation. Another is nano photothermal therapy, the laser will use. Nanomagnetic hyperthermia. and nano ultrasound hyperthermia. So magnetic hyperthermia and radio frequency, what we have done study here. So magnetic hyperthermia is very interesting one that I will show you. How it works, you can see here. So either you can directly inject nanofluid, okay, made of nanoparticle and some fluid, inject in the tumor part and do that RFA, radio frequency ablation. You supply and do the radio frequency ablation. So that is one thing. And in that there is a different techniques to inject. One thing is directly injection, but sometimes it will not work, because if it is in brain, tumor is in brain inside, then injection part is difficult. So you need to sensitize the nanoparticles, put some chemical in that, some ligands in that, and inject from anywhere of the body, and it will reach there. Slowly it will reach. When it will reach to that tumor, then it will get attracted and it will there for few hours. Then you do that treatment. So how to do the treatment? You cannot do RFA, because the electrode also you cannot insert there. Then you need this magnetic hyperthermia. This magnetic hyperthermia is almost, you can say, totally non-invasive technique. There is nothing in that. From outside, you put the magnetic field, and with that high frequency fluctuating magnetic field is there, and with that it will generate heat, and tissue will get killed, tumor tissue. So this is very interesting one. This hyperthermia, magnetic fluid hyperthermia. So for this, I have slides. Again, I will show you in the detail. This sensitizing nanoparticles part, what I was talking about in the brain, how you will do that. So this is generally done by the chemical people. Some types of layer they create on the nanoparticle, and you inject, then it will go to that tumor tissue. Now the thing is, this RFA setup, how to develop this radio frequency ablation setup. It is available actually. Company from, I think we purchased from Germany or something. I don't remember. Okay, so we purchased. It is available, and we tried to make it here in India and less cost, and we developed one setup. So this is electronic circuit mainly, and with the professor at NIT Suratkal, Professor Lakshminidhi, and some more professors were there and doctors, we tried to develop on RFA setup. So we used radio frequency generator, and that we imported from outside, and we used that generator and reached around 300 to 500 kilohertz frequency. This was the circuit what we have done, and we tried to compare with the existing setup, which is commercially available. Commercially available is very costly actually, 15-20 lakh price is there. We purchased that also. And we did this signal generator. We have seen the signal, how it is giving at what frequency. It is going around 384 kilohertz frequency. It is mentioned here, 384 kilohertz, in that range. But as I told you, as you go higher and higher frequency, maintaining power is not easy. So we tried to maintain this power around 30 volt and 60 volt. And power we have got around, if you generally 50 ohm will be the resistance of the tumor there. So 50 ohm, if you say here, we are getting 20 watt only power. Okay, even 20 watt is sufficient to kill the tissue. Okay, but the thing is, safer side, we should develop slightly higher power, so that the controls will be in our hand, we can do treatment in lesser time. So this was the setup what we developed. This is the RFA setup. This was developed at NIT Suratkal under the imprint project. So in this actually, there is a, as I told you, this is also minimally invasive technique, RFA. It is not 100% invasive. So minimally invasive means you have to insert electrode. This is the one big problem here. Electrode you are giving, but if it is a brain tumor, it is very difficult to treat. Okay. So nanoparticle assisted thermal therapy would be a good way to treat tumors with less side effect. So now we will talk on this. So magnetic will go on this. This is this is non-invasive technique. So what we have done in this study, solenoidal and Helmholtz coils for magnetic hyperthermia with intratumoral nanofluid injection. This work was done by my M.Tech student at IIT Patna, Mr. Aditya Gupta, just this year graduated. So conventional techniques are intrusive, painful, and a variety of side effects, we know that. And magnetic hyperthermia is an experimental cancer treatment technique that is a non-invasive and uses heat generated by magnetic nanoparticles, okay, in response to an external alternating magnetic field. The goal is to heat tumor cells to a therapeutic temperature, typically 41 to 45 degrees Celsius, to damage or kill them while minimizing harm to surrounding healthy tissue. Okay, so, and this size magnetic hyperthermia has shown great potential compared to standard cancer therapies, such as radio, chemo, and chemo, due to it's a high biosafety, deep tissue penetration. Deep tissue penetration is very important part here, and selective tumor killing. Okay. Now this part already explained, I think, thermal therapy, different types of therapy, thermal therapy, ultrasound, microwave. Okay, we'll go to the next actually. So in this actually, you want to talk about little bit about the magnetic part. So the compared to other techniques, magnetic hyperthermia is a non-invasive and it prevents unnecessary heating of the healthy tissues because only magnetic nanoparticles get heated. So where the magnetic nanoparticles are there, that part will get heated only. Okay, and magnetic nanoparticles exposed to an alternating magnetic field which generate heat through Neal and Brownian relaxation, raising the temperature 42 to 45 degrees Celsius, causing their destruction. So Neal Brownian relaxation is there, how magnetic nanoparticles get heated. That will come on that. And in this, for magnetic hyperthermia, actually, there are rules, regulations we have to follow. The current supply, what we are giving, this should be in the range of 50 kilohertz to 1.2 megahertz. That frequency, as I was telling you, cannot give 50 hertz frequency. Okay, and that magnetic strength should be 15, maximum should be 15 kilo amps per meter. So this is the magnetic field strength and this is the frequency. So we should operate in between. Magnetic nanoparticles, what I'm using here is iron oxide, Fe3O4, taken from the sigma teaching used. Okay, and this 50 to 100 nanometer particle size is used to magnetic nanoparticle hypothermia experiment, but this what we have done some study here, and as you take the smaller size around 10 nanometer, that SAR value was highest maximum. But if you take, as you go lower and lower, the cost will increase. Okay, and toxicity about this. So if you use gold and all, there is no toxic for the body. But iron oxide is little bit toxic, so special coating layer to minimize the toxicity of MNP, magnetic nanoparticle, is needed. So here in this, there are different people have done different types of coil people have used. So magnetic field you have to generate. So different types of coil people have used so that the uniform magnetic field can be achieved near the or throughout the tumor tissue. That is the main goal. So there are different types of coils. Sorry, we have done Helmholtz coil and uh, solenoidal coil. There are two types of coil. This is the, you can see the third one, mouse here. This is the Helmholtz coil, this type of coil. And solenoidal is this one in the first one, you can see the case. Let's go to that. So this is problem statement here, modeling realistic nanofluid diffusion and comparing the thermal performance of solenoidal and Helmholtz coil under clinically relevant conditions. Here, actually, what the other study people have done is they have considered is nanoparticle injected and it is homogeneously distributed. We have not considered that. We have injected and automatically it will get distributed with time. And so whatever the heterogeneous or whatever the distribution is there, based on that, we started giving the magnetic field, alternating magnetic field, and obtain the performance. These are the difference here. So this is a liver tissue. You can see. It is injected here. You can see the nanoparticle part, magnetic nanofluid, and we are giving these two Helmholtz coils are there. With that, there will be effect and temperature will get, the tumor gets heated, temperature will increase. So there are two types of how the heat gets generated here. There are two things. One thing is Neal relaxation and Brownian relaxation. So two things are there. So Neal relaxation, like magnetizing, demagnetizing. Okay, so that moment is changing internally. So that is the Neal relaxation. Due to that, there is a heat generation. Another thing is due to changing magnetic field, there is a physical moment, physical rotation or movement of the nanoparticle. With that, if it is in a fluid, if it is vibrating or rotating, that will create temperature, that will create energy, heat, and temperature will increase. This is the way. So the model used is laminar flow transport of diluted species in porous media. We have considered it as porous. Yeah, all tumors are porous and that blood flow is there. Darcy law we have used, magnetic fields in bioheat transfer. These are the models used in COMSOL. Here are the equations in bioheat transfer equation, Neal and Brownian relaxation, tau B, tau N. We're using that. We have calculated the heat generation and put in the pen by transfer equation. So this is the mathematical model, and then we have done the modeling and what the data we have taken. You can see the porosity of the tumor is 40% and healthy tissue porosity is 0.2, 20%, you can say. So healthy tissue porosity is more, tumor tissue porosity is, healthy tissue porosity is less, tumor tissue porosity is more. Blood perfusion rate in a normal tissue is more, and and normal tissue blood perfusion is more, as I earlier also explained, and this is good for the treatment of the tumor. And the tumor tissue blood perfusion is less, so that heat what we are generating, it will not carried away by the blood. Blood is less in that, so easy to treat the tumor. This is a good thing. So this is the Helmholtz coil. You can see the tumor is kept between, and healthy tissue is the green one, and tumor is red one. We have done some study here. So 5 centimeter, 5 mm and 10 mm, that size taken, the tumor and healthy tissue. Size maybe mentioned somewhere. Just see. Yeah, here you can see the tumor here 5.5 centimeter means 5 mm and 10 mm the total. The tumor is 5 mm radius. And this magnetic field strength is maintained same in the Helmholtz coil and the solenoidal coil. Okay, 5518 around that much. Here also you can see this is the solenoidal coil. So the thing is, we have to see this. This is axisymmetric type we have made, and here is the tissue part, and you can see the magnetic field is uniform here, almost uniform here. And similarly, you can see in that sorry, this one. Okay, this one also it is like this. So we'll go one by one. We'll see this. This one is first graph. This is the results part. This part is when we are injecting nanofluid, how much time it will be there, that nanofluid will be there in the tumor, nanoparticles. So you can see here, initially with the 0 hours here, and distance also mentioned here. So you can see the up to 4 hours. 4 hours. This is the 4 hours is there. Then this is around 8 hours. Okay, but up to this 5 mm distance. 5 mm is your tumor part. After this 5 mm distance, we are able to maintain around. You can see the concentration here. 120 was the initial, then slowly is going down. It is 100 around after 12 hours. Coming like 100, and it is slowly it is going down if we are going away. So near to the center of the tumor is this part. So this is the time. You can see this is actually, if you are treating 5, then 4 hours maybe good for that. These all things depends on the blood perfusion rate also. The thing is how much time that nanoparticle will be there or will stick to the tumor. Now you can see the magnetic field variation using this solenoidal coil. So magnetic field variation here, you can see this is the Y value. Y value means this is the tumor, and above if you go, the changing the Y value. And this side, right side, if you go, this is changing the X value. So X axis already there, but Y axis is not there. This is magnetic field. Y value is taken in the different, you can see the legend. Y is equal to 0, Y is equal to 10, 20, like that. So this much variation is there. You can see this much variation is there. If you go to Helmholtz coil variation, you can see here this much variation is there. But this 30 mm is far away. So if you leave this 30 mm, other things are variation is less compared to solenoidal coil. If you see the both together, you can see here. Helmholtz solenoidal coil variation you can see here 30, 20, 10 and 0. How this much variation is there? Same thing 30, 20, 10, 0. You can see the variation here. The temperature variation is less. So this is more effective, you can say, Helmholtz coil. The variation of temperature is not that much, it's less. It means that magnetic field is more uniform in this. Here this is for the Y is equal to 20 mm, 20 mm from center of the tumor above or below, it will be same. So at 20 mm, almost both solenoidal coil and Helmholtz coil are giving almost 46 degrees Celsius temperature. Okay, little bit higher in the case of Helmholtz coil, little bit higher. But if you go to 30 mm, 30 mm, y is equal to 30 mm, you can see the Helmholtz coil is still giving very high. Now it is slightly, it is around 46 or above, and this one is dropped to 43 or 44 in that range. So this is the difference. So Helmholtz coil is showing better performance compared to solenoidal coil. So this is the conclusion, final one. So Helmholtz coils exhibit better magnetic field uniformity across the central region and along y-axis, ensuring more consistent heating, even at off-center tumor position. Okay. And at y is equal to 30 mm, 43.6 degrees Celsius we are getting in solenoid, whereas 45.9 degrees Celsius we are getting in case of Helmholtz coils. So this much rise is there. Additionally, you are getting with the same magnetic field. Okay, we are not changing that parameters that side. Okay. So based on these things, you can say this Helmholtz coil is better. Okay, so these are the things. My side. Thank you. So if you have any questions, please tell me.
Rahul, Rahul, हेलो राहुल.
Yes, sir. Yes, sir.
देखो सर कंक्लूड कर
My
दिए.
part is almost over. Now the question answer session. Participants can ask questions.
Yes, sir. Yes. Sir, I have a question.
Yes, please.
Which type of tumor respond best to the thermal therapy?
Which type of tumor is
Respond best to the thermal therapies.
yeah, it is mainly solid tumor, you can say. Okay, so if it is solid tumor, then only this type of treatment you can do.
Okay, okay.
Okay, and suppose it is started spreading, then we cannot control with this anything. Then chemo is the only option.
The second question is, what are the biggest challenge in the transferring lab-based thermal therapy into the clinical practices?
Yes, actually, this type of things is started. People have started using it, and other part means abroad people are using this RFA. Here also in India, also some places it is being used. Our part, one thing is this equipment what we are using here, buying and using. RFA part mainly talking. Magnetic thermia is not, I think, being used. Magnetic part that has some issue also. RFA part is tested and people started using. Okay. So that in that the problem is the one thing is what we use electrode. So electrode machine can be used for the n numbers of patients. That's not the issue. But the electrode what we are using, that for the only one patient you can use, because that once you have used for one patient, using for other like syringe type of thing. But that is not like that much cheaper. This cost around 70,000-80,000 one that electrode. So 80,000 maybe the now price might have increased. I don't know, but we purchased in 70,000 around one syringe type of things, electrode. So that is one issue with the RFA. Another with the magnetic hyperthermia, still in you can say in the research phase. The main reason here is when you are injecting nanoparticles in that, and nanoparticles, what happens when it goes out from that place, that may carry some tumor cells, and there is a chance of spreading this cells in the other organs. So that problem is there, and we are trying to solve that by using smaller size of nanoparticles, and we have to test it whether it will work or not. But if it works, this will be very useful because this is non-invasive type technique. People prefers. Okay, so these are the challenges.
Okay, sir. Thank you, sir.
Thank you. The questions. You have learned something with this or not? Our
Yes, sir.
main
Of
thing
course, sir.
is to something we should learn daily. Something.
Actually, this is the very new things for mechanical engineers.
Mhm.
Uh, how mechanical engineering relate to the biomedical equipments.
Now people are doing this. The thing is, many places our mechanical engineers, electrical engineers, electronics, uh, actually the most of the equipments what the doctors are using, those things we have to develop. Engineers have to develop. So the thing is, our requirement is always there in that, and if we do together research, doctors and engineers, then we'll be able to break through many things, I think.
Yes.
Okay.
Is there is any question from participant side?
My health is not good, so sorry, coughing sound.
I think there is no question, no other question from the participant side.
Okay.
Thank you, sir. It is indeed a great honor to extend our heartfelt gratitude to the Professor Ajay Kumar Yadav, Associate Professor, Department of Mechanical Engineering, IIT Patna, for delivering a truly enlightening and through thought-provoking session on the thermal therapies on the cancerous tumor. Sir, your presentation provide an in-depth understanding of the principal mechanism and the applications of thermal-based cancer treatment, highlighting how engineering innovation can be effectively applied to the healthcare and biomedical fields. The clarity of your explanation and the scientific depth you brought to this interdisciplinary topic have greatly enriched our understanding of bio heat transfer, material selection, and energy delivery in the therapy system. Your insight have inspired participants to explore how mechanical engineering and medical science can collaborate to develop advanced, efficient, and patient-centric treatment technology. On behalf of organizing committee and all FDP participants, we sincerely thank you for your valuable time, expertise, and contribution to this program. Thank you once again, sir, for your expression, inspiring session. Thank you once again, sir. Thank you, sir.
Thank you. Thank you very much. Okay, so shall I log out?
Yes, sir. Yes.
Okay.
Thank you. Good night, sir.
Thank you.
And thanks to the audience for your active participation in this session. We will now take a short break before proceeding to the next session of our faculty development program. The upcoming session will begin shortly and promise to the equally informative and engaging. I request all participants to kindly rejoin on the time at 7:30 after the break so that we can continue our journey of learning without delay. The Google feedback form of the current session will be shared shortly in the group. Thank you.
काही नाही.
मला वाटलं तू स्टाईल कर ढेर खाल्लं देस होता. अरे त्याचं नाव नाही माहित मला. हे कशाला काढलं? हे बिलकुल काढायचं नाही. अरे पेंट करते त्याला सर. बिलकुल हो ना. अबे आयुष्याचं आहे. दारात पूर्ण पाय काढले तुटलेले होता. हे सगळं प्रत्येक सांगत पुस्तक नाही यार. सोन झालं कसं? काय म्हणतो काय करते का? आता नको जाऊ.
काय आणलं पाहुजे रे?